In this video, we're going to be talking about a concept from chapter 1 on bonding and molecular geometry. So there's a couple different kinds of bonds. There's ionic, there's covalent, which is what we'll be primarily dealing with in this class. But remember, there's also things like metallic, which are a little bit different. And there's also other kinds of bonds that are beyond the scope of this class. But for our purposes, we'll be discussing mainly ionic and covalent bonds. So first, to discuss ionic bonds, remember that we're similar to the last video. We're filling shells to be isoelectronic with noble gas notation. So for instance, if we're making a bond between lithium and fluorine, the not denoting that they're in their ground state. The ground state configuration of lithium is 1s2, 2s1, and the ground state configuration of fluorine is 1s2, 2s2, 2p5. What's going to happen is these are going to form their most stable ions, and there's going to be a transfer of electrons between the from the cation to the anion. So there's going to be electrons moving from the lithium to the fluorine. In this case, we're going to take the 2s electron, we're going to transfer it to the fluorine, so it's going to generate a 2p6 shell, and what we'll be left with at the end is we'll have lost one electron from lithium to form lithium plus, so that will be 1s2, and we'll have gained one electron in fluorine to form fluoride, which is going to be 1s2, 2s2, 2p6. So the combination of these two ions to form a compound would be LiF. These are often referred to as salts. So if I ever call something a salt, that's usually an ionic compound. That's a generic name for an ionic compound. And we see that these have both attained noble gas notations. Again, lithium has attained the noble gas notation of helium, and fluorine has attained the noble gas notation of neon. So covalent bonds are a little bit different. So covalent bonds, the electrons are not moved from one to another. They're not transferred, but the electrons are instead shared. So this is more common for organic chemistry. We're more often than not talking about some form of covalent, whether it be nonpolar or polar covalent, and they're represented in many organic species. So for instance, if we have two hydrogen atoms, if we bring these together, we're going to form a bond between them. Those two electrons are distributed equally between the two hydrogen atoms, and we call this a covalent bond because they're shared between both atoms. Now remember, there's a couple different notations for types of bonds. If we share one pair of electrons, I guess we'll just call this a generic. So we can do multiple bonds. If we call this a generic, just X. If we have two electrons shared, we call that a single bond. If we have 4 electrons shared, we call that a double bond. And if we have 6 electrons shared, we call that a triple bond. Remember that as we move down, these are getting shortens, and they're also getting stronger. So triple bonds are stronger than double bonds, are stronger than single bonds, and triple bonds are also the shortest of these three, where single bonds are going to be the longest. Now there's two different kinds of covalent bonds. We have polar and we have nonpolar covalent. And this all depends on the difference in electronegativity. So remember, the trend in electronegativity, if this is a model of the periodic table, is going to go towards fluorine. So fluorine will be the most electronegative atom, and francium over here will be the least electronegative atom. So we say that nonpolar bonds have zero difference in electroneg or electronegativity, where polar covalent bonds have greater than zero difference in electronegativity. So what this means is that something like HH is going to be a nonpolar covalent bond because these are going to have the same electronegativity. So there is a zero difference in electronegativity. We would call this nonpolar. And something like FF or II is going to be a nonpolar compound, a nonpolar bond. We're referring to this bond here now. We call that nonpolar. For our purposes, we also call a CH bond nonpolar. Since the electronegativities of C and H are so close to one another, we do consider this to be a nonpolar bond. And we can combine polarities of bonds together to form an overall polarity of a molecule. So if we're looking at CH4, and we should know by now that this is a planar version of CH4, which is not the actual geometry. All of these bonds are nonpolar, so not only are the bonds nonpolar, but we call the molecule a nonpolar molecule as well. However, if we're looking at polar molecules are going to have an overall dipole, and the dipole is just a difference in poles or a difference in polarity of bonds that do not add up to zero. So for instance, if we have a case where we have water, this is a little more accurate to the geometry of the molecule. We have two polar bonds. We have two OH bonds. These are going to be polar bonds because there is a difference in electronegativity. When we draw the dipole arrow, which looks like this is going to be our delta plus, and this is going to be our delta minus side of a dipole arrow. In this case, O is more electronegative than H, so we would draw the dipole arrow pointing towards O. We do that on both sides. And if we look, these arrows are going to overall total to a dipole that's pointing towards the oxygen. So we would call this a polar molecule. Now, there are cases where we can have polar bonds in the molecule, but a nonpolar molecule overall. So, for instance, if we look at the molecule CF4, if we look at this molecule, we see that all of these bonds are polar. It's a CF bond, which is a polar bond. If we draw our dipole arrows, they're all going to be pointing towards the Fs because that's more electronegative than C. However, if we look at these overall, we see that the opposite dipoles are going to cancel out. So the overall dipole of this molecule is zero, so this would be a nonpolar molecule. So we can have some cases where if the dipoles cancel out, then we do not have a polar molecule. We end up having a nonpolar molecule. Now, to consider the pole of a molecule or the dipole of the molecule, we do have to consider molecular geometry, which is governed by VSEPR theory, which is valence shell electron pair repulsion theory. What this says is that electrons are going to repel each other to form the most stable, furthest away configuration in a given molecule. So that's why water is not linear. This is why water, in fact, adopts this bent configuration. I would encourage you to review the names of the particular geometries. In our case, we're going to be most interested in the tetrahedral base and the trigonal planar base. Those are going to be our sp3 and sp2 hybridized centers. So if we look at this, we see that CH4 is not planar like we described over here, but it's instead in a three-dimensional shape. We call this tetrahedral. And the bond angle in a tetrahedron is going to be 109.5 degrees. If we're to remove any one of these, we generate different types of geometries. So for instance, if we have NH3, that has a lone pair. This is going to be in our electron geometry of tetrahedral, but now we are not in the tetrahedral molecular geometry. We call this trigonal pyramidal. Again, if we get to water, which is like removing two sets of electrons or two sets of bonds from a tetrahedral set, we again call this bent. So these are going to be important ones to remember in organic chemistry. The other one that's going to be important to remember is going to be this base here. So I'm just drawing, this is formaldehyde. If we have this arrangement with three bonds around the center, we call this one trigonal planar. And if we were to remove one of there, we would call it bent. Again, this one is a little bit more obvious, but if we have something that is straight across, we would just call this linear. So these are going to be the most important geometries for organic chemistry, especially the tetrahedral centers, as these are usually sp3 hybridized, and the trigonal planar centers, which are usually sp2 hybridized, and again, the linear, which are usually sp hybridized. But we will talk about that in a future video.